Hello everyone, this is lecture 22 of PTRE 465531. We uploaded the grades. It was 7 students. The lowest grade was 7. The highest grade was 70. The average grade for the class was 45. It was a little bit lower than what I expected, but everything was low. So it's good for you guys in the sense that it wasn't like somebody making 95 and then everybody else making low. So when I curve at the end of the semester, and I prefer curving at the end of the semester and not exam by exam, it would be easier. But that being said, I mean, some people did like very low, like they really, I got the impression that they didn't even know what we were doing. So I'm talking about the exam.
Oh, okay.
Do you know what was the average? 45.
Geomechanics?
This class, yeah. So that being said, okay, if you didn't do a good grade, it might not be a grade that you don't, it might be a grade you didn't like, but it's not necessarily a bad grade on the grand scheme of things. So don't worry necessarily about the number. It's just like, think about it, you need to change something. And sometimes it's not changing something, doing something hard, it's doing something being smart about maybe the way you revised wasn't appropriate, maybe, or efficient enough, maybe the way you went over the material, etc., etc. And we are gonna try to, also myself, I'm trying to see what questions that were the biggest issues with. There are some questions you are gonna see similar next exam, but I think the next exam is mathematically more simple. And because I think most of the long problems, all the long problems of exam number 2, they really are related to one equation only. And we are gonna have a homework on that equation and some simple equations that I think it would be fine eventually. It's just I don't want you to, how do you call it, to don't get don't give up and don't get a grade that is so terrible that cannot be fixed, because you might do well in the second exam, you might do well in the final exam. I will see what I can do for that. The other thing is that, okay, since I don't know if the timing of the exam was an issue, I thought about removing one question to make it easier for you on time, but it would have been an easy question being removed. So I would have removed easy points, which is, it's again not smart taking easy points out of the exam, you know, because I'm lowering the total number of points and then you are, so what I can do, I can go and talk to the administrators. Normally this is not allowed, because if the exam is in a 50 minutes lecture, it has to be a 50-minute lecture if it would be an exam taken during that time. But since there is no on-campus students taking the exam, I can talk to the administrators and make the second exam 75 minutes to take the timing factor out, and I will still make it a 50-minute exam, basically. It will be a 50-minute exam, but you will have 75 minutes to do it, because I already wrote the exam, sort of. So I will make that easy to take out completely the time factor for the second exam. Because I'm thinking maybe some people, they saw some things they didn't understand, or they looked difficult and they got stressed, and that's why they did it. Then the timing was on their head. That's why I'm gonna try to take the factor of time completely out of the second exam. And what else can we do? Yeah, the rest will be during the review, but you still have to do it. I mean, you have to be comfortable with the stuff that we learned. The equations that we looked in this particularly in this, maybe not module 2, but the remainder of the class is pretty easy, pretty straightforward. It's like high school level. You don't see any derivative or anything or an integral or something. It's just very, very easy stuff. So don't get discouraged. Like Malek said, I mean, still you can do well, and there will be curve. And think about it like if the highest grade was 70, say that we make that 100 or something. I'm not saying this is how I'm gonna curve, but if you had a grade in the 50s, it becomes like 80, kind of. It becomes higher. So, but what I do is that I will curve the final grades of the class, like the whole grade as the weighted average for the whole, basically. And we see. Last time we finished talking about shear failure, we saw something very important, which was the Moore-Coulomb diagram. We have this picture from Miss Gono's thesis. I think now is in the East Coast doing something related to data analysis. She used the Moore circle to indicate how does injecting salt water in Fort Worth Basin, in the Fort Worth Basin, can get the faults, pre-existing faults in the vicinity of those injection wells close to slipping, and basically you have earthquakes. And then you get bigger and bigger fault slipping, and then bigger slippage, and then you get basically the failure, the earthquakes that everybody is observing, and they realize initially they blamed hydraulic fracturing, and then they realize it's not hydraulic fracturing, but it's a byproduct of hydraulic fracturing, which is tons of salt water that had to be dealt with and got reinjected underground to the Ellenberger formation, and they basically they cause earthquakes like crazy. So that was a very important topic that I breached last time, and we are going to be seeing that even in the next class of what is it, well completions for the undergrads and advanced stimulation techniques for the graduate students, which is more advanced, sorry, more applied version of what we do.
So how do you measure the event of?
The what?
Oh,
Tough?
yeah.
You measure it, that's a good question. You measure it indirect, okay? You do not apply that.
You apply stress.
You apply S1 and S3, and together they make tough. So the biggest tough S1 and S3 can give is this. So you understand this? The biggest the difference between S1 and S3, let me write it on the board for the people online. Very good question, actually. Okay, you apply this, and you get maximum you can get is this tau max. Okay. Now I'm not applying directly tau and everything else, by the way, from 0 to tau max. I'm applying S1 and S3, and I'm getting the shear. So it's an indirect application.
Yeah, but how you measure the shear? Is it
How do I measure?
yeah, like you apply, you have one axis.
Well, I need to have a criterion. It's very easy. I cannot measure it directly. It's not like it's not indirect because I'm not applying this shear. It's not like I'm having this fault and I'm pushing it like this and I'm measuring how much force I'm pushing. It's not as easy like that. Because I'm applying compressive stresses, S1 and S3, and I'm getting shear like as a indirect effect.
Yeah, but the shear is like the stress on the failure plane, right?
Yeah. Yeah,
Oui.
exactly.
Tangent sur le stress.
Yeah, yeah, yeah.
Yeah, that's good.
Yeah, very, very good question, actually.
Top zero is when you have top zero
Impact.
is
When it's intact.
intact.
Yeah, the core is intact. I can take the core, put it in the air, put it like this, and it's basically it's intact. It doesn't have pre-existing fractures.
So it's hard to for failure.
Yeah, it's hard to
That's top O, right?
stuff. Oh,
Yeah.
that's the y-intercept that you are seeing.
Yeah, but I was thinking like top equal to top O plus mu sigma.
Yeah.
I was thinking is when you have pre-existing pressure,
Okay,
consolidated or not,
pre-existing fractures.
fractures, yeah.
It depends on the extent of those pre-existing fractures. Generally, we use Zobac's nomenclature. If you say pre-fractured, it implies that taf not equals 0.
That doesn't equal zero when you have pre-existing fracture.
No, it does.
It does.
Yeah. It's not intact.
Means that it's easy for failure.
Yeah, you have planes that are easy to fail.
So how you can determine the top O then?
It has to do with the material, the rock. Generally, to do it, you need to take a small sample so that you do not have the chance for a crack in it or something. Generally, the cores that we are doing in the UCS testing and this kind of level, we consider them intact rock samples. And you will see a lot of papers of geomechanics people saying experimental investigation on intact rock samples.
Because
That's what they
all
mean.
the geomechanical tests, they were asking for impact force.
Yeah. I think the difference is in scale mostly. If we want to measure a rock as big as this room, probably we can say pre-fracture. It has enough critical faulting stress hypothesis can be valid because it's a big enough volume.
So more you have fractures, more the top zero is increasing, that's what you mean?
No, it's
No,
decreasing.
decreasing. Yeah, decreasing. More likely that it will go to 0.
Yeah,
It's like more, it's
I
like you need
understand.
less stress to fail.
Yeah,
you
it's
don't need stress to fail, yes.
and actually Lundstern was very, very big proponent of the critical faulting stress hypothesis. He was saying it's very valid.
Because in structural geology, when they are talking about value stresses, try to put all the stresses one after the other.
Yeah,
And the most of that, they will see the different strays that you can find in the fault plane, dipping plane, how many strain, like stray you have, like,
okay.
because after the another time of straining, you will just do reactivation. You will not create factors most of the time.
Yeah, okay. So you reactivate all the ones.
Yeah,
that
you will see
existed.
how many movements you got in the plane of the fault,
Oh,
and you can decide.
yeah.
And you can see, it will give you a hint how many like polystrand like had this area.
I see.
Because the professor, he was telling us it's hard to break then move.
Yeah. Of course.
It's easy to move.
They'll break.
They'll
Yeah,
break.
of course. 100%. Because in hydraulic fracturing, we say it's easier to propagate than initiate, right?
Yes.
It's
same.
better to initiate and propagate an old fracture that started already than making a new one. Starting a new one, it's a higher pressure needed.
Refract.
That too, but also if you have like one stage and you are trying to pump multiple clusters, if one cluster shoots a fracture early, it's easier to propagate that fracture that already started than starting a new one from another cluster. And that's why you end up with dominant fractures or runaway fractures. Basically, one stage giving one huge fracture, and then the other rest are.
In the field.
Yeah.
People, they like that.
No, they don't like that, but they see that. They don't want that.
Exactly. Because
They don't want that. Yeah. Seismos, I saw a picture by Seismos. They were doing microseismic or something, and they had that. It looked like one dominant fracture per stage, basically.
It's not good, it shows all the pressure of the.
No, it relieves, yeah, it uses all the pressure. It's like you are providing a conduit for the fluid to move.
Yeah,
And then it basically prefers to go there than make the bigger job, you know. Anyway, then we talked about Mr. or Doctor, I don't know, Barley. 1978, he did experiments on very big blocks of rock, and he found that for the stuff that we are talking about, mu is about 0.6 to 0.8. And if he had to put a point at one of the two edges of the how do you call it, the spectrum, he would do this. He would say 0.6. 0.6 is a pretty accurate, it's pretty good. Like you wouldn't expect it to go beyond 0.8 or too much less than 0.6. And let me see. Okay, here. Cemented, we're going to talk about, okay, just like we talked about the Brazilian test for tensile. It was fairly simple. Now, what about the UCS? Like, sorry, what about the shear failure? Because remember the Brazilian was shear failure. Now, what about, sorry, the Brazilian was for tensile failure, I apologize. Now, what about the shear failure? We are gonna talk about the UCS test or the unconfined compressive strength test, which is also carried out in a, how do you call it, in a triaxial loading frame, like the one we have in our lab. That doesn't work, I think. The triaxial doesn't work for some reason.
which three axle?
The one at the back.
Uniaxial.
No, triaxial.
Only worked. The triaxial that one.
Oh, okay.
Do we have triaxial?
Yeah,
We have uniaxial, no?
it's not called uniaxial, it's called triaxial.
Triaxial.
That's why the real triaxial, they call them true triaxial. It's triaxial, but I remember also telling us, like, it's called triaxial cell, right? But you apply one stress.
Yeah.
You can put a vessel and have a confinement.
It's like, yeah, you put three stresses, but the lateral stresses are zero.
Yeah.
So then they autolog what they call it.
And the autolap has triaxial stress ability, but it's not, the true triaxial is the stuff that, how do you say, like my old advisor in Corel School of Mines was doing, that you really apply SV, SH max, SH min. Those you call them true triaxial,
True, yeah.
and there is less than 10 in the whole world. There is one in Halliburton from the 80s. There is one in Mobile that my old advisor put together also.
They use cubes, right?
They use cubic model. There is a low stress one in Texas, 1 by 1 cubic feet basically, and they use how do you say when they want to lift the car after an accident, flapjacks for applying the stresses. It's like you have to make one. If you want to, you have to build one. You are not gonna buy one. Whereas the loading frame, the triaxial, is just on one direction. You just buy one. Anyway.
And there is one used to calculate the strain, not the stress.
Yeah, LVDT.
VDT with like elongation.
Yeah, you can put that on the triaxial. You can, it's like it's one thing that you screw on the plate, and it has like a thing that is holding, staying steady. And then you have the LVDT, which measures like displacement.
Yeah.
That's how we had that in the.
It's like you have your phone and it doesn't apply stress. It's like it's elongate.
Yeah. It's very easy to add to a setup through triaxial setup. This one very easy, very easy. It's
LVDT.
Yeah. LVDT is just that thing that moves up and down. What does this do?
Cause
Low voltage, low voltage something transducer, deviatoric transducer, something like that.
Because on that project of South Carbon, they were very interested on that. I don't know why.
Yeah, if you have to measure displacement, yeah, you do that. Anyway, so cemented rocks can bear shear stresses with zero effective lateral stress. So I can apply stress on the top, and then on the side, I have zero. So basically, I have the same issue I had before, the same scenario I had before, sorry, not issue. But now, what am I doing? It's like I have a rock, this is the plate, this is the thing on the top, made by steel. Remember, Newton's third law, can't go away with it. The plate moves up, and so you apply the same stress here, basically, until it breaks. Now, look at this. The LVDT is something that goes on the plate, like this, and it has a thing that looks like this. Okay. And then it's holding with a stand. Oops, sorry. This is I'm sorry. Because for the students to understand what we are talking about. And then this is the LVDT. And it has a needle that touches down like this. Okay. And this is like a suspension. It can move up and down. So as the plate moves up, the needle gives you a reading of displacement. It's like it moves up and down very, very easily. Very, very easily. That's what goes there. Very, very simple. If we were in Texas, I would have shown you, but we don't have it here. I didn't see an LVDT. But yeah, this is what it's. And you don't need to know it, but LVDT. It's basically a transducer that is measuring the distance. This thing is like a spring that moves up and down, like a pen. Because as the plate moves up and the rock is stressed, it becomes shorter and shorter and shorter. You can measure the stress and the change in the height of the sample. You have an idea of the Young's modulus, right? But eventually, what is going to happen? The rock will break. It will break at a 60-degree angle. It will either break like this or break like this. Yeah. What you will determine is unlikely that the crack is going to happen at the same time. But what happens is that Spinoza used to do that. He will take the sample after it broke, and he will take it to students, and he will be like, look, you see tendencies of failure both like this and like this. What will determine which side is going to go is heterogeneities, pre-existing facts, and stuff like that. But it's going to be a failure like this. It's going to be either like this. Yeah. And it will crack. Now it will crack at a certain sigma 1, which is what you apply. Let's call it sigma 1, 1. And then on the outside, you have sigma 3, 3. I don't care about sigma 2 because my Moore Coulomb failure criterion doesn't care about sigma 2. Now, what is my sigma 3 in this experiment? 0, exactly. Yeah, 0. 0, okay. So if I plot, let me use black to avoid confusion. I don't know what those are right now, but okay. I have sigma 1, 1. Where is my sigma 3? On the origin, right? So now what I'm doing is basically this. Okay. And what is my sigma 1 is basically what I will call the UCS of the sample. Okay, now, suppose I have an equipment, I modify this equipment, and there are vessels you can make, because you know the triaxial experiment is carried out in empty air. You have space. You can, if you have a good machine shop people like we did have in Texas, we ask them to make vessels, and you put the sample in the vessel, and it has a seat for the sample. And then you fill the vessel with water, and somehow you apply a sigma 3, okay? So the sigma 3 is basically, since we are talking about water, let me use watercolor. Sigma 3 is like this. Okay, with a pump, I'm pumping water of a certain pressure. Now the sigma 1 that I will need is gonna be somewhere here to break. It's no longer, sorry, what did I do? It's no longer a UCS. An even bigger difference, like it's a confined strength test. And it's much, much bigger. But the UCS is an important value. It's a quick test. It's a little bit slower than the Brazilian test. If you carry the test at the same rate, it will be slightly, it will take a little bit more time, few seconds more. You don't care about.
But the value, is it the same?
No, the value would be much bigger. The UCS would be like 10 times bigger than the something like that. Yeah, much bigger actually. Yeah,
Exactly.
yeah. It's easier to break in tension than yeah, much bigger. It's the opposite of spaghetti. Spaghetti, they say, is like they say carbon fiber is like spaghetti. You can pull it, it's fine, hold tension, and then you try to compress it and you make a mess. This is the opposite. The rocks are the opposite. Like they are better in tension. They are worse in tension than in glass is like that, basically. It's brittle. Okay, let's see what I wrote here. UCS is the maximum compressive stress applied in the axial direction the rock can hold under unconfined conditions. Axisymmetric tests require rock samples in which the length should be about twice the diameter to minimize shear end effects as in short samples and buckling instabilities as in long samples. So you want a sample that won't bend to the side. Like you don't want this to bend like this too much.
Yeah.
And you don't want it too short that it's gonna cause what we call shear. Huh?
Shear and different.
Yeah. Basically, the shear on the surfaces to be too dominant. It's like we have capillary end effects in core flooding. If you took petrophysics, very, very similar.
That's why you need to have your core longer.
Yeah.
For innocent and perturbation stuff.
Yeah, for the UCS test, 1 inch diameter, 2-inch length makes sense. And this basically shows what I drew earlier. It's he was using sigma A for axial, and I put sigma 1 on top of it, and sigma 3 here. There is nothing on the sides, right? Okay. So sigma 1 is basically the UCS, unconfined compressive strength. What about confined? Oh my God, what is going on here? Application of an effective compressive confining stress, maybe using a pump or something. We don't care about how, we care about, let me make everything visible to avoid, huh? You don't care how you apply, you care there is a sigma 3. The sigma 3 is no longer a 0, right? I applied on the side somehow. Okay, so now I'm gonna need an even bigger axial stress, an even bigger confining stress. And this is what they used here. And of course, with a linear shear failure criterion, which is basically the more Coulomb failure criterion, you will get an angle, a fracture, like I said earlier, at 60 degrees from the maximum applied stress. Oh, it already shows it. Yeah. So I was gonna draw something, but it's already drawn. Okay. Sigma A. Oh, for us, this is sigma 1 minus sigma 3. We don't know yet what is sigma. It's axial minus radial. But in this case, the radial is the confining, which is sigma 3. Yeah, because he has it. This is from Spinoza's notes. This is sigma 1. This is sigma 3. This is epsilon 1. And yeah. And it's no longer confined. So, because the students don't know yet the cylindrical stresses, I use sigma 1 and sigma 3. But basically, sigma 1 is the most compressive. Sigma 3 is the least compressive. The difference between the two, the bigger the difference between the two, the bigger the path that you can apply.
And the S0 is the top zero?
Yeah, in this case. That's what he's using. The nomenclature he's using, sorry, in his notes. I think he wrote a book or he's writing a book. The measured peak stress is higher than the peak stress without confining stress, obviously. That's what you see here. I'm going very high, not before, compared to before. The increment in the peak stress depends on the internal frictional strength of the rock. Hence, the maximum shear stress taf is a function of both the rock's cohesive strength and the effective normal strength, which takes us back to the equation we had before for the more Coulomb. And let me clean everything because it's. Now, I have a slide explaining something that I already did explain. I'm like, okay, the rock is not like this, is not like the cores, because the core samples, they are intact. The rock is very big, it's heterogeneous, it has a lot of pre-existing fractures, heterogeneity, anisotropy, etc. So you can assume an infinite number of faults facing in every direction, in all directions, basically.
DFM basically.
Huh?
DFM number basically.
DFN is more like you create them. Those are natural. Discrete fracture network. Yeah, I mean, extensive fracture network, but natural fractures facing in all directions. So if I'm injecting here and I have a favorite, the easiest way to fracture is a fault facing this way, being stressed at this value, I have, you know? That's what the assumption is saying. Very important assumption. They can be loaded at any stress. In a formation with faults at a variety of angles to the current stress, the faults are hydrologically conductive today, or the faults that are hydrologically conductive today are those that are critically stressed in the current stress field. The critically stressed fault hypothesis posits that faults that are mechanically alive are hydraulically active, and faults that are mechanically active, mechanically dead, are hydraulically dead. It basically tries to say what I was trying to say with more scientific language. It basically says that it's a statistical thing. If you have a bigger sample, you have bigger number of faults. And if you have a bigger number of faults, you have more chances to have different phases, like angles, and then you have a different chances to have different stress environments, right? So hydraulically dead means they are not conducting. You cannot basically move fluid through them.
It means that any mechanical fault has a hydraulic bath.
Yeah, of course. But if you put water or fluid there, you can make them reactivate, right? It can be assumed that in any pre-fracture formation, if you see this word pre-fracture formation right underneath in an exam or something, yeah, very important. Simplifies your equation very easily. You can find a PEF that is favorably oriented and critically stressed, i.e. is just ready to sleep, ready to sleep. So I will say this is the most important point of the slide. Forget about the rest. Just remember critical faulting stress hypothesis. It means this. It means this. And then pre-fracture formation means this. Very, very important. Very, very important. Oh, we have 4 minutes. Good. I might be able to introduce this very important equation. In situ stress test stability, considering shear slippage along PEFs. Okay. Now the question is, we talked about in situ stress states, right? We talked about SV, SH max, SH mean. We also talked about them in terms of S1, S2, S3. They're the same thing, it's just different nomenclature. And they mean different thing. They mean more or less the same thing, I mean, but the different definition. Now, let me ask you a question. What about, you can think, if I ask you to write down combinations of stresses, SHV, SH max, SH mean, you only need to make SH max bigger or equal to SH mean, right? Yeah, bigger or equal to SH mean, that's the only rule.
Okay.
Right? And then the SV is vertical and the other two are horizontal. Yeah. But the only rule in terms of magnitude is SH max is bigger or equal to SH mean.
Yeah.
Okay. How many permutations or combinations of stress states you can write?
9.
No?
Repeat again.
Yeah. If I will give you a pen and a paper, and I ask you to write sets of stress states, in situ stress states, as VSH max, SH mean.
3 mean.
Yeah, 3 numbers. How many sets of 3 numbers you can write? The only rule is that SH max is bigger or equal to SH mean.
Yeah,
Yeah. How many can you write?
only
No. You can write infinite. Right?
81.
No, infinite. Isn't the SV equals 70, SH max equals 60, SH min equals 40?
Okay, you are talking about the number.
Yeah.
You are talking about the state.
As long as SH max is bigger or equal to SH min, it will be correct, right?
Yes.
Okay.
It's about the regime. Are they put SV on the right or on the left?
Yeah. That doesn't matter.
The 3 regimes you will include, then you have 9. I was thinking that.
But the no regime SH min is bigger than SH max, right?
That's why we have only half of polygon.
Yeah. We are ultimately getting to the polygon. That's why I'm mentioning this. So now a question is, how many of those that you write down, you have a page and you wrote infinite number of sets of stress states, right? Okay, I want to ask you a question. How many of those are stable in the Earth subsurface? And the answer is not all.
Okay.
Not all.
Okay, yeah.
How do we know that they are unstable there are several ways. What we can do in this class and what we do generally in our work as geomechanics people is that we assume that if there is a pre-existing fault in this stress state, will it slip or not? If there is a fault that will slip in this particular stress state, I will say, Mr. Malek, the stress state you wrote down is unstable. So I don't expect to see that in the Earth's subsurface. It's not likely that I will see it in the Earth's subsurface,
Yes.
right?
Yes.
Okay, because, and you ask me why, I will say because if a fault exists under those stress state conditions, it will automatically fail in shear and it will cause an earthquake, right? So I'm telling you that this stress state you wrote is not likely to be correct, to exist. It's correct, but I don't expect to see it.
Because we have no earthquake.
Yeah,
Yes.
because it won't be stable.
Yes.
And then you are gonna ask me, but how do you know that a fault exists under those stress state conditions that is stressed at this level, ready to sleep? How do you tell me that under those conditions I have a fault that is critically stressed and facing at the optimum direction, ready to sleep? And I will tell you because of the critical faulting stress hypothesis.
It means that your circle is crossing the line.
Yeah, it means that I have a fault that is ready to sleep under any given conditions. So it's like I don't want to say a dirty example. Like if I leave my phone outside and I go to the restroom, I'm in a cafe and I leave my phone outside on the table and I go to the restroom, I can assume if I'm in Los Angeles, I need to assume that there is a thief ready to steal it, right? I don't care if there is a thief ready to steal it. I will assume that there is somebody who's gonna steal it. Okay? But I'm in LA. It's likely. In Grand Forks, I can leave it and go home and come back and it will be there, right? Or I can tell somebody to watch it for me. It's the same thing here, in a sense. Okay, I'm assuming worst case scenario. I have a stress. I have a critically stress fault there. So I'm just gonna test whether this stress state that you gave me, S1, S2, S3, or SV, SH max, SH min, is gonna cause it to slip.
It means in more cycle, they are all below the line.
Yes. They are all. No, don't think of more circle.
Because that's why, yeah, if you have the line defined for your rod, any stress you apply that have a circle that is half circle that is behind the line, below the line, then it means you are stable.
Yeah, you are stable in that case. Yeah.
And that's
Yeah, I want it to be below the line.
yeah, that depends
Of
on
course.
on the slant of your, which is mu, right? Depends on
Yeah.
the slant.
It depends on that. But we are not gonna use the Mohr circle. We're gonna use the same equation for the Mohr circle, but in a different form. So we're gonna say the stability of faults against shear slippage, frictional failure, is given by this condition. And this is the most important equation for your exam number 2. That I was saying earlier. This is the same equation as this. It's the same equation. Oh, I'm sorry. I hope she's not waiting outside, but this is important topic. So this is the same thing as saying tau for stability is this. This is the same exact equation.
Right?
That's me, right?
Where is the, you're asking where the tau O is. Where is it?
Okay, because we have PEF.
Yeah, it's gone.
Yeah.
So I don't have tau O.
Yeah.
I only have this and this. Okay. And for a conversion to Cartesian coordinates, because we know the tau is not a directly applied value. It's a value applied by S1 and S3. I use this version. There is a way. I used to know how to, when I was undergrad, how to go from how to this. And then basically, it's the same equation.
The sigma n is the one in the middle, right? The middle of the circle.
The sigma n, no, it's the x-axis.
Yeah, but if you apply sigma 1 and sigma 3, your sigma n will be the one in the middle of the circle, right?
No, sigma is the x-axis. It's the whole x-axis, it's a variable.
Yeah, but
The shear is-
but the normal stress in terms of sigma 1 and sigma 3, what is it?
Sorry? Oh, the middle, you know.
Oh, the
middle.
midpoint? Yeah. When
Some
you,
people say it's S2.
oh, no,
No, it's not
S2.
S2. No, S2 is different circle.
I saw
No,
people
it's
say
not
it's-
S2.
It says 1 minus S3 divided by 2, something like that.
Yeah, it is.
It's part of the derivation.
Okay,
It's part of the derivation.
because geometrically is, it's.
Yeah. It's like you do that times sine 2 theta. And
It's
then-
actually sigma 3 plus the radius of the circle.
Yeah. Sigma 3 plus the radius of the circle. Yeah. That's true.
Because, well, why I thought that, because most of people say that S2 is close to S1, like more
Oh.
far than the middle.
Yeah, so it's not
Um,
sigma n.
Yeah, and some people says that it depends on the regime of your failure.
Oh,
And when you have like sigma 2 in the middle, like in the center of the circle, that means that you have a shear regime.
I don't know about that, but I know you can use different criteria as well,
Yeah, I mean,
depending on, because there is the Hagen-Brown criterion, which is a little bit different, but the more Coulomb is the most common for this kind of stuff that we're talking about. So I will use, so we said Malik gave me a number and I told him it's unstable. Then he asked me, why do I think it's unstable? And he told me, and I told him, because if you have a fall under those conditions that is ready to sleep, it actually will sleep. And then he asked me, how do I know that? And I say critically faulting stress hypothesis, right? The only things that I care about here is S1 and S3 that he gives me for pressure that I might be able to figure out or given, and then mu. So 4 variables, something like that. So let's finish this slide and we will go. The left-hand side is basically the same as sigma 1 divided by sigma 3 or sigma 1 divided by sigma 3. I'm using only one value because I'm assuming they are principal. And the right-hand side, I only have one mu, basically only depends on mu. And remember, it assumes that what I said earlier is true. All faults are critically stressed. And because the right-hand side only depends on mu, if I take Barley's equation, I can put 0.6 here, and I get 3.12. And I can put 0.8 there, and I get 4.33. So ultimately, this equation becomes sigma 1 divided by sigma 3 equals 3.12 to 4.33, right? And that's what I will solve, or basically, I mean, we use this thing for stability. If the left-hand side becomes bigger than this, I have failure. I have an earthquake. I need to be below. I need to be less less than this to be good, to be stable. And we are going to demonstrate it graphically next class with a very, very important concept. The second most important concept in this class, the second most difficult, I guess, concept in this class, which is the stress polygons. And with that, thank you very much. Huh? Yeah, I mean, it's important.
It's very important. It's
Yeah.
very important.
Stress polygons are very important.
And more many people know it.